Hi, this is Aksa. I'm a PhD student at CMU, and I'm going to present my work on analyzing third-party dependencies in modern web services. This is a collaborative work with my advisors, Vyas Sekar and Yuvraj Agarwal. The study is motivated by a DDoS attack that happened in 2016 on a DNS provider named Dyn. There are a lot of lessons to be learned from this attack, particularly its root cause, and as I show in this talk, we can expect more Dyn-like attacks in the future. During this attack in 2016, a lot of popular websites such as GitHub, Spotify, and Twitter were inaccessible to users for many hours. Here is an outage map of the attack. In total, 178,000 domains went offline and tens of millions of users were affected. The list of websites that went down goes on. It includes almost all the popular services we know. So how were the attackers able to bring all of these down? This was possible because all these websites, such as Netflix, exclusively relied on Dyn, a third-party DNS provider that acted as their authoritative name server. As a result, when the authoritative name server was down, a lot of websites were inaccessible to millions of users. Attacks like these raise many questions about the resilience of the internet. How easy is it to bring down the internet? Particularly, we need to understand how prevalent these kind of third-party dependencies are. For example, how many other websites are at risk of Dyn-like attacks? Are there other hidden dependencies that we also need to know about? There might be interservice dependencies, which indirectly affect a website. And finally, since Dyn attack had such a huge impact, it is natural to think that websites would adapt as a result. How has the world changed in using third-party services as a consequence of the Dyn attack? For example, did websites stop using Dyn, or did they start using multiple providers? To answer these questions, we analyzed top 100,000 websites, Alexa websites. Alexa is an external service that ranks websites by popularity. Alexa rank is calculated from a combination of daily visitors and page views on a website. To see how the world changed in response to the Dyn attack, we look at the dependencies of top 100,000 websites in 2016 and 2020. In this talk, I'll first describe our measurement methodology to measure the third-party dependencies of websites, and then explain our main findings. Then, after the findings, I will also present some recommendations in light of our findings, and finally, some limitations of our work. To start with the measurement methodology, we first need to identify the services which are crucial for a user's access to the website. To do this, we look at the life cycle of a web request. When a user makes a request to a website, it first goes to the authoritative DNS server, which provides the IP resolution of the website. After the IP resolution of the website, user starts a TCP handshake followed by an SSL handshake if the website supports HTTPS. If yes, then the website provides a certificate which is verified for revocation by the user by contacting the OCSP server or CRL distribution points set up by the certifying authority. Finally, if the certificate is valid, the user requests the content of the website page. If the website is using a CDN, then CDN will serve this content. Based on this, we identify three services. The first one is DNS, the second one is certificate validation by certificate authority, and the third one is CDN. Note that these by no means are the only services that a web request encounters, but we just identify these three services and define the scope of our work. Given these services and websites, we need to identify what exactly we want to measure. So we are interested in third-party dependency of a website. For example, here, the website TechRadar uses another entity, Let's Encrypt, as its certificate authority. Next, there might be indirect dependencies between websites and service providers. For example, here, Let's Encrypt uses Cloudflare as its authoritative name server, and hence TechRadar has an indirect dependency on Cloudflare. We are also interested in critical dependencies, which exist if a service provider is integral for a given service. For example, here, if Cloudflare is down, OCSP servers of Let's Encrypt will not be accessible. Hence, Let's Encrypt has a critical dependency on Cloudflare. In case of DNS and CDN, we compute critical dependency by measuring if the website is redundantly provisioned, which means that the website is using multiple DNS or CDN providers. And in case of certificate authorities, we compute it by measuring if the website has enabled OCSP stapling. Here, TechRadar does not support OCSP stapling, and hence TechRadar has a critical dependency on Let's Encrypt as well as Cloudflare. If OCSP stapling is enabled, the user doesn't have to contact the OCSP server for certificate validation. So Let's Encrypt will not be contacted here. But if OCSP stapling is not enabled, then users of TechRadar will have to contact the Let's Encrypt OCSP servers to validate the certificate. Now, given this, we first describe our measurement methodology for DNS. What we essentially want is to find the authoritative name server of each website. This can easily be done by looking at the name server's resource record of a website. Then we want to identify if this name server is private or a third party. I would go into details for this in the next slide, that how do we actually identify if it's a private or a third party. And finally, for a website and its name server, we want to identify which of these name servers belong to the same entity. For instance, here, Azure DNS and O365 filtering both belong to Microsoft. So since live.com is using these two which belong to the same entity, it is actually not redundantly provisioned. To identify third-party name servers, prior work looks at second level and top level domains of the name server and the website. If they match, then the name server is private, otherwise third party. For example, here in case of Google, its name server also has the same second and top level domain, google.com. Hence, it gets correctly classified as private. However, this fails in case of YouTube, where the name server gets classified as third party when in fact it is not. Other approaches look at the start of authority DNS records, which contain administrative information about the DNS zone. If the start of authority record of the website and the name server are the same, then it's private, otherwise third party. This works in case of YouTube, but it fails, for instances, in case of Twitter, where it is using a third-party name server, and its start of authority is also that third party. For instance, here Twitter is using dynec.net, which actually belongs to Dyn. To cope with these issues, we add a few more heuristics. So for all website and name server pairs, we classify the name server as private if the second level domain and top level domain match for the website and the name server, or if the name server is present in the subject alternate name list of that website. SAN list is present on the HTTPS certificate of a website, which tells that this certificate will also work for the domains present in the SAN list. Hence, it's a good way to know if a given domain is private or not. If the start of authority do not match, we classify it as third. And finally, if the name server serves more than 50 websites, then we say that it's more likely third party. In general, we identify approximately 10,000 third-party DNS providers in our data. For measuring CDNs, we fetch the web page of the website that we want to measure the CDN of, and then we extract all the resources in the web page and identify the resources which are internal. For example, for reddit.com, this resource that comes from redditmedia.com is an internal resource. We use TLD matching, start of authority, and subject alternate named lists here as well to identify internal and external resources. We do this because internal resources, if they come from a CDN, then it means that the website is actually using a CDN. For all the internal resources, we fetch their CNAME records. If the website is using a CDN, then these CNAMEs will point to the CDN. For instance, here, the CNAME actually points to Fastly. We input this CNAME to our CNAME to CDN map, which will output Fastly here. We manually build this map by taking help from available CNAMEs on the internet, on the CDN's websites, and also in public suffix lists. After we have identified the CDN being used by a website, we also need to see if the CDN is private or a third party. And to do that, we again use TLD, start of authority, and SANS list to see if the CDN is private or third party. In general, we identify a total 86 third-party CDNs in our data. For certificate authority dependency, we just fetch the certificate of a website, and from that extract the links for the OCSP servers and the CRL distribution points. And we use the same techniques, which are TLD matching, start of authority, non-matching, and SAN list to identify if these are third-party certificate authorities or not. In our data, we identify a total of 59 third-party certificate authorities. Now we present our main findings. I will start by answering the question, how prevalent third-party dependencies are and how concentrated different third-party providers are. Overall, we find that 89% of the top 100,000 websites use third-party DNS, 32% use a third-party CDN, and 76.8% use a third-party certificate authority. Moreover, 85% critically depend on a third-party DNS provider, 28% critically depend on a CDN provider, and 59.5% critically depend on a certificate authority. For DNS and CDN, it means that they're using just a single DNS or CDN provider, and for CA, it means that they do not support OCSP stapling. All in all, we found that 89% of the top 100,000 websites critically depend on a DNS, CDN, or CA provider. In addition to this, we also found that critical dependencies are higher for less popular websites. For example, we observed that 49% use a third-party DNS provider in the top 100 websites and 89% in the top 1,000 websites. Same is the case for critical dependencies. For instance, 27.9% critically depend in the top 100, while 84.8% in the top 100,000. This means that more popular websites care more about availability. Now, since third-party dependencies are very prevalent, it raises the question of how concentrated various providers are. The greater the concentration, greater will be the single points of failure. This is a dependency graph of website to DNS dependency, where each edge shows the dependency of a website on a third-party DNS provider. The size of each node here is proportional to its in degree, which in the case of DNS provider is the number of websites using it. We observe that the topmost DNS provider, Cloudflare, alone serves 23% of the top 100,000 websites. In general, we observe that only top 3 serve almost 40% of the websites, when the total DNS providers we observe are almost 10,000. This indicates the DNS space is highly concentrated. We see similar trends in CDN, where the topmost CDN provider, Amazon CloudFront, alone serves 26% of the websites that use CDN. Particularly, we observe that only 3 CDNs serve almost 60% of the websites that use CDN, which are CloudFront, Akamai, and Cloudflare. The situation for certificate validation is also similar. DigiCert alone serves 28% of the websites that support HTTPS. Particularly, only 3 certificate authorities, DigiCert, Let's Encrypt, and Sectigo, serve 60% of the HTTPS supporting websites out of the total 59 certificate authorities we observed. To summarize, our main findings were that third-party critical dependencies are highly prevalent and third-party services are very concentrated. A direct implication of this is that 89% of the websites are vulnerable to DINE-like incidents. A single provider can affect as much as 25% of the top 100,000 websites. Now the question is, if this is the complete picture, or do we need to take indirect dependencies into account as well? And this brings us to our second question, which is, are there any indirect dependencies between websites and their third-party providers? To do this, we first need to analyze inter-service dependencies between DNS, CDN, and CA providers. In case of CA to DNS dependency, we found that out of the 59 CAs that we observed, 48% of them use a third-party DNS provider. In case of CA to CDN dependency, 36% used a third-party CDN provider. Moreover, out of the 86 CDNs that we observed, we found that 36% use a third-party DNS provider. Hence, third-party dependencies are also prevalent among service providers. In case of critical dependencies, we found that 31% of certificate authorities relied on a single third-party DNS provider, 36% relied on a third-party CDN provider, and 17% CDNs relied on a single third-party DNS provider. These critical dependencies between service providers give rise to indirect dependency. But why should we care about indirect dependencies? I mean, okay, sure, they exist, but what's the harm? Turns out that as a result of indirect dependencies, we see huge amplification in the impact of a given provider. For example, in case of CA to DNS dependency, Cloudflare now critically serves 37% of the top 100,000 websites as compared to 24% before. And in case of DNS made easy, the impact goes from 1% to 23%. Hence, because of these indirect dependencies, we see amplification of provider concentration. To summarize, critical dependencies are also widespread among service providers, and these dependencies can amplify the concentration of service providers, which means that the effect of single points of failures in the internet is amplified, and a single provider can now impact 37% of the top 100,000 websites. This is what we observed for our data in 2020. Now we see how the world changed after the DINE incident by comparing 2016 dependency data with 2020 data, which brings us to our third question, which is, how did the world change after the DINE incident? Did websites try to reduce their third-party dependency on service providers? Did the concentration among providers decrease? We observed that critical dependency in DNS increased. With respect to CDN and CA, we see no significant change in the critical dependency. Similarly, in case of inter-service dependencies, we observe an 8% decrease in critical dependency in CA to DNS dependency, and a 4% decrease in CDN to DNS dependency. So overall, in terms of provider to DNS dependency, we see a decreasing trend, which is encouraging. Now let us look at the change in concentration of service providers. According to this figure, in 2016, 2,700 DNS providers served 80% of the websites, while in 2020, only 54 providers serve 80% of the websites. This means that we are in general moving towards more concentration. This is not an encouraging result because it means that single points of failure actually got bigger. And we see similar trends in CA providers while concentration decreased in CDNs. To summarize, we see no significant change in the third-party dependency trends among websites. We do observe a decline in third-party dependency among service providers. We also observed that services became more concentrated in 2020 as compared to 2016. All in all, we do not see an increasing trend in redundancy. We did observe that websites using DYNE were more redundantly provisioned in 2020 as compared to 2016. But in general, there was no significant trend towards redundancy. And because the concentration of providers increased in 2020, single points of failure actually got bigger. Now, based on these findings, we make some recommendations. For websites, they should consider redundancy while using a third-party provider. Moreover, they should try to understand their indirect dependency arising from the inter-service dependencies of the providers that they're using. Similarly, for service providers, they should make it easy for websites to be redundantly provisioned. As we observed that many DNS providers do not support redundancy. And also, service providers should try for redundancy in their inter-service dependencies. Finally, service providers should also try to be more transparent about attacks on their infrastructure. To highlight some of the limitations of our work, our measurements are from a single vantage point only, and hence we may miss region-specific dependencies. We analyze dependencies only on the landing page of a website, hence we may miss dependencies that manifest deeper in the content hierarchy. A direct consequence of this could be that we may miss certain CDNs used by a website because their landing page didn't access any resource from a CDN. Finally, we also did not look at the physical and networking infrastructure dependencies such as routing and hosting, mainly because it's not the scope of this work. To summarize, the DDoS attack on DYNE in 2016 raised some questions about the resilience of the internet. In our paper, we try to answer some of these questions, particularly about the prevalence of third-party dependencies and their impact. To do so, we analyze top 100,000 popular websites. We also look at their inter-service dependencies to get a holistic view. And we identify the potential single points of failure in the internet. We see that third-party dependencies are highly prevalent. Indirect dependencies amplify provider concentration, and we do not see a move away from third-party dependency after DYNE incident. The code and data used in this paper is actually also available online. Thank you so much.